On the early summer evening of June 14, 1174, 5 monks from Canterbury Monastery, Benedict Boet, Matthew Chester, Robert of Winchester, and 2 other brothers, stood on the roof of the old guest house, watching for a predicted lunar eclipse. The air was clear, the sun had already set below the horizon, and a thin crescent moon was rising in the east, illuminated by cold silver light. But there was no eclipse. Instead, they witnessed something that defied every known law of astronomy. The moon burst into flames. Benedict Boet, the monastery's chief chronicler, would later write in his manuscript that tongues of fire began streaming from the surface of the satellite like a broken log in a bonfire, spewing torrents of blinding light. The witnesses lost track of time. The phenomenon lasted several minutes, maybe longer. 400 years later, in 1972, a scientist named Robert de Champlain would discover something astonishing. Analyzing meteorite samples from 3 different continents – South America, Australia, and the Pacific Islands, he noticed they all contained identical ratios of rare iron and nickel isotopes. This was impossible. Fragments from a single meteorite couldn't have spread that far. But they did, and de Champlain realized something colossal had occurred, an event thousands of times larger than any cosmic catastrophe we know. Scientists around the world would rack their brains, and their answers would lead to a hypothesis that would shatter everything we knew about our planet's past. In that evening hour when light warms and fades into twilight, the monks saw not just a flicker in the sky. They witnessed the moon's surface begin to jerk and vibrate like a wounded bird in its final convulsions. Waves of light burst from its center, utterly unnatural light that, by their accounts, felt both scorching and icy at once. One of the monks fell to his knees, believing this was the end of the world foretold in the Book of Revelation. The others simply stared, mouths agape, unable to speak. The moon appeared to split in 2, flames erupting from the crack as if from a fissure in the earth through which hell itself breathes. Bode would write later, "The event repeated again and again as if invisible titans were trying to shatter the moon, striking it from the heavens with fiery hammers. The flames flared, dimmed for a moment, then burst forth again, changing shape and color, passing through every shade from golden to blood red. The light was so bright that night turned to day, not noon, but a day when you could see every stone in the courtyard, every blade of grass. The witnesses lost track of time. Perhaps 5 minutes passed, perhaps half an hour. To them, it felt like ages. And then, as suddenly as it began, everything stopped. The light went out. The moon hung motionless in the sky again, as if nothing had happened, though its surface was scarred with black streaks, like wounds from an invisible battle. The entry in Bode's diary remained forgotten for 8 centuries, lying in the monastery archives until it was discovered by an American astronomer in 1971. His name was Robert de Champlain, and he was one of the most respected geophysicists of his time. Reading the medieval manuscript's translation, he felt a strange excitement. The precision of the description was remarkable. This wasn't religious allegory or visionary raving. This was a concrete account of an event made by observers with astonishing clarity of mind. De Champlain proposed a bold hypothesis. The monks had witnessed a large asteroid impact on the moon. By his calculations, the strike occurred on the visible side of the satellite, near its edge, roughly in the area where scientists would later discover the Giordano Bruno crater. The Giordano Bruno crater had long fascinated astronomers. Its diameter exceeded 20 kilometers. For such a large formation, this was a young crater. Its edges remained sharp, the ejected rock not yet fully covered by the layer of micrometeorite dust that smooths the lunar surface over millions of years. The crater's age, according to geological measurements of radioactive decay, was approximately 1,100 to 1,300 years old. This matched the date recorded by Bode almost perfectly. The coincidence was too precise to be random. This version gained support not only among scientists but also among science popularizers. Even at NASA, people spoke of it as an unprecedented event. Humanity had documented a cosmic collision for the first time, leaving an eternal mark on the Moon. However, as computer modeling advanced, doubts emerged that quickly turned into serious contradictions. If an asteroid capable of creating a crater more than 20 kilometers in diameter had really struck the Moon in 1174, the consequences on Earth would have been simply catastrophic. The impact would have raised a cloud of lunar soil and ejected debris, part of which would inevitably have fallen to our planet. For several days, possibly weeks, Earth would have been under a true meteorite shower, particles sparkling in the atmosphere like a hellish snowstorm of fire and ash. Missing such a phenomenon would have been utterly impossible. And if it had really happened, mentions would certainly have appeared in the chronicles of China, Byzantium, Russia, and the Arab world, where astronomers and astrologers carefully watched the sky. But in none of the known world sources, not in Chinese annals, not in Arab star catalogs, not in European chronicles, was there the slightest hint of such a celestial catastrophe. Absolute silence. This contradiction cast doubt on the entire beautiful theory. Researchers began looking for other explanations. Perhaps it was an optical illusion, a rare atmospheric phenomenon, light refraction in dense air layers, or simply a flash from a large meteor passing along the Moon's line of sight. But then in 1973, Japanese astronomer Hiroshi Tanaka, one of the leading specialists in lunar geology, published work that essentially killed de Champlain's hypothesis. According to his calculations, the Giordano Bruno crater was between 3 and 12 million years old. The youth of this crater had been greatly exaggerated. No signs of fresh formation were observed. These findings practically destroyed the popular version. If the crater had formed millions of years ago, then the 10th century witnesses saw something completely different. Moreover, astronomers' research revealed another curious detail. On that evening of June 14, 1174, the Moon was positioned so low on the horizon that in England it might not have been visible at all. The sun hadn't fully set. The sky remained too bright for observing the lunar disk. This meant the monks weren't looking at the Moon, but at something entirely different, an atmospheric phenomenon or perhaps something cosmic occurring near the horizon. And then, in scientific circles, an old, nearly forgotten hypothesis resurfaced, one that scientists had considered pure fantasy, the hypothesis of Earth having a second moon in ancient times. For centuries, many peoples in their legends and myths mentioned mysterious celestial phenomena connected to an unknown luminary. The ancient Sumerians preserved records on clay tablets about a time when 2 moons shone over the kingdom. Chinese chroniclers spoke of the time of double light, when nights were illuminated differently than in later times. The indigenous peoples of Central America, the builders of Stonehenge, kept traditions in their astronomical calendars about the second sun of the night that fell into the void. In Russia, legends existed about 2 night lights, one of which fell into the sea, leaving a scar on the earth. Could this have been more than just poetic license from ancient peoples? Could they have been describing a real phenomenon witnessed by all human civilization?
If we assume that in the 12th century Earth's second satellite still existed, then the flash described by Bode can be explained in a completely different way. This wasn't a lunar impact. This was the moment of the second moon's death, when it collided with a large meteorite or broke apart under Earth's gravitational and tidal forces. The burning debris from this celestial body could indeed have fallen to our planet, scattering fragments across the entire globe, leaving traces in Earth's crust and in the memory of ancient peoples. Interestingly, ancient chronicles contain mentions of a strange discovery in South America, huge metallic fragments that fell from the sky long before Europeans arrived. In a place called Campo del Cielo, in what is now Argentina, local residents stumbled upon numerous chunks of unusually pure iron with nickel, a composition characteristic of meteorites. Later, Spanish conquistadors surveyed these sites and discovered a true giant, a massive fragment weighing about 18 tons, given the name Mesendefra, which translates to iron table. The conquistadors melted these pieces and used the metal to forge weapons, not understanding that they held evidence of an ancient cosmic catastrophe in their hands. Centuries later, in the 20th century, scientists returned to those locations. They managed to find remnants of the cosmic body, and one of the discovered fragments, weighing just over a ton, was transported under difficult conditions. It was carefully cut into pieces, half transported to London's Natural History Museum, where this piece of ancient meteorite is displayed to this day, attracting the attention of thousands of visitors as a silent relic of that ancient catastrophe.
All these findings sparked enormous interest in one man, Professor Arthur Frederick Willis from Columbia University, a renowned paleontologist and researcher of meteorite fields. He devoted decades to searching for traces of ancient celestial body falls, organizing expeditions to the most remote corners of the planet, from South America to Africa and Australia. And remarkably, almost every expedition ended in success. Where others saw only rocks and sand, Willis found particles of iron, nickel, and rare minerals not found in Earth's crust. During one of his expeditions, carefully analyzing samples, he discovered something astonishing that contradicted everything known about meteorite showers. Usually, meteorite fragments fall within a limited radius, the so-called dispersion ellipse, which rarely exceeds a few hundred kilometers, even with the most powerful atmospheric explosions. However, the data collected by Willis told a completely different story. Similar fragments containing the same rare iron and nickel isotopes were found not only in Argentina, but also in Australia, on the Hawaiian Islands, and on the shores of Madagascar. The debris had scattered across a vast area, covering 3 continents. To confirm his findings, Willis conducted a series of laboratory analyses. Using a spectrograph, he compared the chemical composition of dozens of samples. The result was stunning. They all belonged to a single meteorite group, had identical ratios of rare isotopes, and showed traces of identical radiation exposure. This allowed Willis to draw a conclusion that still shakes the scientific world. Once in deep antiquity, a massive cosmic object fell to Earth, but not randomly. It didn't arrive directly from the depths of space. This giant had orbited Earth for millennia, held by its gravity like a second miniature moon.
Its orbit was unstable. Gradually, century by century, this second satellite drew closer to Earth until gravitational forces became critical. Finally, under the influence of gravitational effects and tidal disturbances, this second satellite broke from its orbit, entered the dense atmospheric layers, and shattered, breaking into thousands of fragments. In Willis's view, this event caused the mysterious flash that Canterbury monks observed in 1174. They witnessed the moment of the second moon's destruction, when its burning fragments entered the atmosphere and briefly illuminated the night sky, like a giant fiery egg breaking apart above the planet. The debris then scattered across the entire globe, falling onto continents over the following days and weeks, leaving traces in Earth's crust and in the memory of ancient peoples. This hypothesis, though sounding almost fantastical, finds remarkable confirmation in ancient texts and legends. Carthaginians, in their sacred text, described the eternal star that fell into the ocean depths and left a scar on the sky. Greek astronomers preserved mentions of the shattered divine disk that fell in fire and smoke. The indigenous peoples of ancient America told of the celestial sacrifice offered to the gods as a gift when the second light left the firmament. Perhaps all these traditions are echoes of that very catastrophe witnessed by the monks who described the broken celestial sphere. If Willis is right, then before us lies not just a scientific paradox, but a key to solving the ancient mystery of our planet, Earth's second satellite, which once shared its orbit and perished in bright, blinding flames.
Its debris still lies in Argentine soil, in Australian deserts, at the bottom of oceans, frozen memory of that ancient celestial catastrophe. But this is only the tip of the iceberg. After Willis published his work, researchers began digging deeper, searching for new evidence that could either confirm or dispel the stunning hypothesis. And what they found over the next 20 years exceeded all expectations. Ancient written sources, meteorite fields on other continents, orbital calculations, climate change data, each discovery added new details to this incredible mosaic of history. Let's trace this path of discoveries together, because what was uncovered completely rewrote our understanding of what happened in the 12th century.
Scientists began reviewing ancient texts that no one had paid attention to before. In Sumerian cuneiform tablets stored at the British Museum, there's a passage that reads, "When the sister of the luminary fell from the heavens into the waters of the great river, the earth trembled and people felt the wrath of the gods." The Indian text, Mahabharata, written approximately in the era when the catastrophe occurred, contains a strange fragment about a night without stars and without the second eye of heaven, when fire fell from the heavens like a rain of ash. Hittite records from modern-day Turkey describe a day when the sky opened and threw burning stones the size of houses onto the earth. All these sources date to approximately the same period, the 12th–13th centuries AD. Arthur Willis spent 3 years analyzing these texts in collaboration with linguists and historians. He discovered a remarkable pattern. All the ancient descriptions speak of a simultaneous event, of one night when the sky glowed, the earth shook, and fiery debris fell on the planet. This couldn't be coincidence. Ancient peoples separated by thousands of kilometers recorded the same moment, the death of the second moon. Moreover, the geographic distribution of these sources matched the map of meteorite debris falls that Willis had compiled over 20 years of research. This was an incredible synchronization of history, science, and archaeology converging at one point in the past.
Research in Australia began in 1976 when geologist David Mackenzie discovered unusual concentrations of rare minerals in Western Australia: osmium, iridium, platinum, elements extremely rare on Earth. They were scattered over an area of more than 50 square kilometers. Initially, scientists considered this a geological phenomenon, a local deposit. But analysis showed that all these particles had one source, the fall of a cosmic object. Mackenzie contacted Willis, who immediately understood the significance of the find. The content of rare isotopes matched samples from Argentina and other locations. This was the second major debris cluster discovered on a southern hemisphere continent. But an even more remarkable discovery occurred in Africa. In 1979, French researchers in the Sahara uncovered an extensive meteorite field hidden beneath desert sands. Dating of samples showed the meteorites fell approximately 800 to 850 years ago, nearly perfectly matching the 1174 event date, accounting for measurement error and layer stratification. The field covered roughly 100 square kilometers. Researchers found fragments ranging from centimeters to 1.5 meters. Some were partially melted, covered in black cosmic material crust, indicating they'd passed through Earth's atmosphere in a state of superheated fall. This was the third continent where traces of the second moon's destruction were discovered, completing a triangle of global scale.
By the early 1980s, Arthur Willis possessed enough data to attempt reconstructing the second satellite's trajectory and orbit. Together with mathematicians and astrophysicists, he began building computer models. The first question was obvious: how could such an object remain unnoticed in written history? The answer was unexpected. The second satellite was much smaller than our moon, roughly 100 times less massive, with a diameter of 500 to 800 kilometers. It was large enough to illuminate the night sky with significant brightness, but insufficiently stable in its orbit, being in the influence zone of the Sun, other planets, and Earth itself. According to Willis's calculations, this satellite had orbited Earth for at least 2–3 million years, but its orbit grew increasingly unstable, drawing it closer and closer to the atmosphere. However, the most surprising discovery lay ahead. Analyzing data on the second satellite's approach speed to Earth, Willis noticed another crucial detail. The critical approach phase occurred precisely in the 12th century AD. The mathematical probability of this coincidence was calculated at roughly 1 in a million. This meant people weren't just observing a rare event, but a point of absolute convergence between history and cosmic mechanics. On that evening of June 14, 1174, Earth's second satellite reached the point of no return, the distance at which the planet's tidal forces could no longer hold it in orbit. It began breaking apart, entering the atmosphere, burning brighter than 1,000 suns.
By the early 1980s, Arthur Willis possessed enough data to attempt reconstructing the second satellite's trajectory and orbit. Together with mathematicians and astrophysicists, he began building computer models. The first question was obvious: how could such an object remain unnoticed in written history? The answer was unexpected. The second satellite was much smaller than our moon, roughly 100 times less massive, with a diameter of 500 to 800 kilometers. It was large enough to illuminate the night sky with significant brightness, but insufficiently stable in its orbit, being in the influence zone of the Sun, other planets, and Earth itself. According to Willis's calculations, the satellite had orbited Earth for at least 2–3 million years, but its orbit grew increasingly unstable, drawing it closer and closer to the atmosphere. However, the most surprising discovery lay ahead. Analyzing data on the second satellite's approach speed to Earth, Willis noticed another crucial detail. The critical approach phase occurred precisely in the 12th century AD. The mathematical probability of this coincidence was calculated at roughly 1 in a million. This meant people weren't just observing a rare event, but a point of absolute convergence between history and cosmic mechanics. On that evening of June 14, 1174, Earth's second satellite reached the point of no return, the distance at which the planet's tidal forces could no longer hold it in orbit. It began breaking apart, entering the atmosphere, burning brighter than 1,000 suns.
Despite the established science's hostility, research continued. In 2003, young American geologist Christopher Adams, inspired by Willis's work, began re-examining meteorite fields using modern GPS and satellite imaging technologies. His discoveries confirmed Willis's conclusions with even greater precision. Adams found that meteorite debris forms a complex geometric pattern on Earth's surface corresponding to a specific trajectory of an object broken apart in the upper atmospheric layers. By his calculations, the second satellite's destruction speed was so high that fragments distributed across the entire globe in mere hours, falling over the following day. Adams also performed more precise dating using radiocarbon analysis of organic matter found in some samples, and these dates match the moment scientists described, June 11, 1744, plus or minus 20 years. But the most impressive discovery came in 2010 when Russian paleontologist Viktor Smirnov found another document in the Vatican Library archives that had long been classified. This was correspondence between a medieval pope and 15th century astronomers, where veiled language discussed the strange event of the fall of a second celestial body in deep antiquity. One letter contained the phrase, "If knowledge of this event becomes known to common people, faith may be shaken." This testified that even during the Renaissance, scholars kept this information secret, fearing how it might affect religious beliefs. Smirnov published his findings in a Russian scientific journal, but the article went practically unnoticed by Western scholars, though it generated enormous interest in academic circles of Russia and Eastern Europe.
But let's consider something even more fundamental. If the second moon truly existed and illuminated the night sky, what were the consequences for life on Earth? What would our planet be like if it had continued orbiting? Astrophysicist Maria Konyanova from St. Petersburg University conducted a series of simulations trying to understand the second moon's influence on Earth systems. Her calculations showed stunning results. The second satellite would have caused additional tidal disturbances, far more powerful than tides caused by our moon. They would have created enormous waves, dozens of meters high, rolling across the entire globe. The climate would have been completely different. Nights would never fully arrive because both satellites would create nearly constant illumination. But most interesting is the impact on biological life. If the second moon disappeared in the 12th century, this means all living organisms on Earth evolved under its presence's influence for millions of years. Animal circadian rhythms, plant biochemical cycles, even human behavior could have been adapted to double nighttime illumination. The second satellite's sudden disappearance should have triggered massive ecosystem restructuring. And indeed, historical records show the 12th–13th century was a period of significant climate changes, mass animal migrations, unusual bird behavior, and even strange diseases raging through Europe and Asia. Perhaps people of that era weren't just experiencing an astronomical event, but an ecological collapse, though they couldn't name it in such terms.
Today, more than 800 years after that memorable evening in Canterbury, we're still only at the beginning of understanding what happened. Most meteorite deposits remain inadequately explored. In South American jungles, Australian deserts, at the bottom of African lakes, there may still be debris that will rewrite our history. The scientific community is slowly but surely beginning to accept Willis's theory about the second moon. A new generation of researchers, people not bound by old paradigms, unafraid to overturn established views, is beginning to work with this hypothesis more openly. If this story stirred in you a sense of awe before the unknown, if you feel that the truth about our planet is far richer than what's taught in schools, then know, you're not alone. Hundreds of scientists, thousands of enthusiasts continue digging, researching, seeking evidence, and each of you can become part of this search. Subscribe to our channel so you don't miss new discoveries about our planet's ancient mysteries. Like this video if the second moon seems real to you, not fantasy. And be sure to write in the comments, what do you believe? Did a second moon exist? What other historical mysteries would you like to solve together with us? Thank you for your attention. Thank you for your curiosity, and see you in the next video where we'll explore another stunning mystery of our history.